We're going to continue with our review packet, page 2. Yeah. Okay, is anybody missing the review packet from? Very good. Okay, how far do we get with page 2? 6. Okay. So we didn't, did we get through number 6 or?
Yeah, we got
We got the 6. All right, so we'll continue with 7. So let me just make sure that we're on the same page with the quiz. So your quiz will be front and back, very similar to the layout on for worksheet 1. When we get through worksheet 1, we'll continue through worksheet 3. I did worksheet 2 during the morning review session, and I have it recorded. Okay, and then tomorrow morning, I will do a help session, 7:15. I'll go over worksheet 4, in addition to any questions that you guys have, so we can always revisit any of the problems from in the packet if you have any questions tomorrow. So your quiz will be 2 pages. It'll be one of each topic, so we'll have to know how to find critical values, EBT, Rolle's theorem, mean value theorem, first derivative test, okay, test for concavity, second derivative test, and then sketching a graph, and we'll focus on, we'll get some more practice with that today. Okay, so we got done with 6, so let's look at number 7. Number 7, find the intervals where the graph is concave up and concave down. We know that all of this is going to come from the second derivative function. So we're going to work our way down to the second derivative function. So we find f prime first, and then we make our way down to f double prime. Okay, from f prime, we keep going, make our way down to f double prime. Find our critical values, critical points, set our second derivative equal to 0. Solve for x. Negative 2/6 reduces to be negative 1/3. Okay, we place negative 1/3 onto our concavity sign line, second derivative sign line. Okay, and then we test values in each sub-interval. So I'll choose a value to the left of negative 1/3. I'll choose a value to the right of negative 1/3. We're testing this against the second derivative factor, or don't have to necessarily factor, it's easy enough. So plug in negative 1, I get a negative value, so I know that my first interval is going to be concave down. Plug 0 in, I get a positive value, so concave up. So I know I have 2 subintervals. One interval is concave down, the other is concave up. And then is there a point of inflection? Yes, because there's a change in sign on either side of my critical point. So before we filled this second derivative sign line out, all we knew was that negative 1/3 was a candidate for point of inflection, but we didn't know for sure that it was until we see that there's a sign change. So The -1 and 0 is no longer going to be used. We don't want to include those numbers in any of our statements. All we're using is negative infinity, -1/3, and positive infinity. Okay, so we go ahead and practice writing out our statements. Our function is concave up. Our for the first interval, sorry, second interval, our graph is concave down in that left interval, and there's a point of inflection. If I asked you for that point, how would you find the y value? Original, good. And you can use your calculator. I may ask you for that, but it's just you're just entering into the calculator and getting that y value, and then pay attention to your because statements. Okay, I'll specifically indicate in the directions for you to write out your because statements. Go ahead and practice writing that out. Okay, are we good with 7? Question.
The POI, the y value, you plug it into the original.
Good, that's right, original. Okay, I'll move on to number 8. The key is in your packets. Okay. Okay, all right, so here's number 8. If our function is given here, there's a bit of a typo here. That should be in -20x. Change that there. Okay, -20x, -10. Okay, second derivative test. Let's recap what this is. So the second derivative test it does the same job as the first derivative test. The point of it is to use the second derivative to find max and min. So that's our goal. Our goal is to find the max and min. Relative max, relative min. Same goal as the first derivative test, but obviously going to be a slightly different method of going through it. Okay, so first thing is we're going to find f prime, and we're going to do the same things that we did with the first derivative test. We're going to find f prime, set f prime equal to 0, find the critical values, but rather than creating the slope sine line, we're going to go through a different procedure to decide whether those critical points are max, relative min. Okay, so f prime. Okay, go through power rule. Okay, factor. Take out a 2. Go through star method here. Multiplies to be 8 times c, that's -30. Adds up to be -1. So two numbers that multiplies to -30 is 5 and 6. And then I wanted to add up to be -1, so I'll make it -6 and +5. Reduce. Okay, so there's my f prime. I'll set f prime equal to 0, solve for x. and I get x equals 2, and x equals -5/3. Okay, so here we have our candidates for relative max, relative min, but normally we would do this, right? Normally you would create a slope sine line, you would test your interval, and then you would decide whether you're going to get a relative max or relative min, right? Maybe you'll get a positive slope, negative slope, positive slope, and you'll conclude -5/3 is a relative max and 2 is a relative min. We're not going to go through this method. We're going to go through another method here. So we're going to apply the second derivative test, but we're going to make the same conclusion about 2 and -5/3. Okay. So what we're going to do is you're going to find f double prime. I'll roll again. 6x squared becomes 12x. -2x becomes -2. Okay, so this is what's different here. We're going to take these critical points from f prime, and we're going to insert them into the f double prime. Okay, we don't want to set f double prime equal to 0. If we do, that's something else, right? That's test for concavity. We're using specifically the second derivative function to test the critical points from f prime. Okay, so then f double prime of 2. I'll insert 2 in first. I get 22. Okay, the number is not that important. What's the important thing here? Is that it's positive. Okay, so let's verbalize it. A second derivative positive value means what? Concave up. Okay, so if you can write out those words and then give yourself a visual, concave up looks like a U. And if you look at the point that is involved with concave up, you're staring at a what? A relative minimum. Good. So we can say relative minimum at x equals 2. If we went through the first derivative test, we will get the same result, but we're purposely using second derivative method to arrive at this conclusion. Okay, go with that. Okay, f double prime, we're going to test the other point here, -5/3, into the second derivative function. Okay, so 12 divided by 3 is 4. 4 times -5 is -20. -20 minus 2 is -22. The important thing is that it's less than 0. Okay, so let's verbalize it. This must mean that this graph is experiencing concave down. Okay, let's visualize it. Concave down looks like this, which means that the important point here, there must be a relative what? Max, yeah. At x equals -5/3. Okay. If you don't verbalize it and draw a picture, you may make a mistake because the tendency is students, they see that 22, they're thinking, oh, positive, that must be a bigger number, it must be relative max. Oh, negative is smaller, that must be relative min. And that's where students mix it up. Okay. But if you can verbalize it, oh, this is concave up, and I can make that decision.
Would you rather be one that like it's too positive now?
Yeah, that's possible. If they're both positives, then you have 2 relative mins.
You have to looks like absolutely.
Oh no, there's no absolute min here or absolute max here. That's with EVT. Here we only care about the relative max, relative min. We don't care about the overall value of it. Yeah, we just care about those particular hills and valleys. Okay, any questions with second derivative test? Good, all right. Graphing. Okay, we haven't done these sketching problems yet, so we'll do a couple of these, make sure we're comfortable with them, because you will see on the quiz tomorrow. Okay, so we're going to sketch a labeled graph of a function. So we have all these characteristics. We're going to translate these characteristics onto a slope and concavity sine line so we can kind of visualize pictures of it. And then we'll kind of step by step graph a picture of it. Okay, first thing here, f of 0 equals f of 2 equals 0. These are nice order pairs. They're giving us some points to kind of anchor our graph a bit, but we know our graph has to go through these 2 points. Okay, 0, 0, and 2, 0. Okay, let's look at the second statement here. F prime of x is greater than 0 if x is less than 1. Okay, can we verbalize it in a way that feels more visual here? What is f prime of x greater than 0? What does that mean? Okay, positive slope. Okay, where's positive slope going to occur? Okay, what's another way of saying less than 1? Right, left of 1. Which, yes, will include negative and 0. But I like to do this as well. I like to just kind of give a visual perspective of this. So why don't we create a slope sign line before we sketch the graph? We know we have positive slope to the left of 1. Now, if they ever mention an x value, that's an indication that it's a critical point, and there's going to be something happening at those points, either a peak or a valley or an asymptote, something. So you want to include whatever x value they give you onto your slope sign line. And I want a positive slope to the left of x equals 1, so I want to kind of get a picture going. Okay, f prime of 1 does not exist. What does that mean? Okay, so either vertical asymptote or sharp turn. Okay, it doesn't specify. So if it doesn't specify, you can actually decide which one you want to do. Either way, if the slope doesn't exist, yeah, sharp turn or vertical asymptote or hole. Okay, doesn't. There's a lot of things that we can. I'm going to say sharp turn. It just feels more. When we talk about slope that doesn't exist, but vertical asymptote will be fine as well. Okay, f prime of x is less than 0 if x is greater than 1. What's another way of saying that? Yeah, negative slope to the right of 1, right? So here we go. We can go ahead and fill out the rest of our slope sign line. Okay, we also have information about the second derivative sign line. Okay, can we put this into words? F double prime is greater than 0. What does that mean? Concave up. Where's the graph concave up? Good, everywhere except 1. Now they do mention x at 1, so that does give you a hint that you do want to include that onto your concavity sign line. So concave up everywhere except at 1. So what can we put over here? Concave up, and then to the right, concave up as well. So we're kind of, it's nice to have these kind of visual cues to help us with our graph. So let's go ahead and create our graph. I'm going to start with what's easy here. I can plot my order pairs 0, 0, 2, 0. Okay, I don't want to do too much at once. I think it's easier if you can kind of break this up. So let's do a rough sketch. This is not, let's just do a light trace of the graph. I just want to kind of get an idea where my graph is going. Then I can kind of go back and give it the nice curvature that it needs. So I know my graph is going to be increasing up until some value of 1. I'll create a sharp turn there, and then I will make the graph decrease after 1. So, and I have to go through these points. So I don't care about my curvature. I just want to get my slope going. And also it's nice to know where the path of the graph is, because whatever you do with your curvature, you're not going to veer too far away from the path. You may make some curvature cleanups along the way, but we know we're not going to have the graph completely off course. So this kind of keeps us in line in terms of where our graph is going to be. Okay, so I'm just looking at this here. I know my graph is increasing. I'm expecting a relative max at 1, a slope that is a sharp turn, or a slope that doesn't exist with a sharp turn and decreases. Okay, so now I'm going to go back and trace over this graph. So this is what my real graph is supposed to be. I want the graph to be concave up while increasing. Now, understand that we're not going to do a full U because I need my graph to be positive slope. So I'm only going to be showing this portion of the graph. Does that make sense? If it's concave up, I don't have to show the entire concave up shape. I just have to show it in relation to my restrictions here. I know my graph is increasing. So the best I can do is this. Right. I don't want to get the full U going because if I do, then I'm breaking with what I know to be true, right? I don't want a negative slope here. I want this whole thing to be positive slope. But it is showing me, it is matching that curvature. Okay, sharp turn. And I still want concave up. So I'm just going to plot this piece of it here. Concave up, curvature, but I never want the graph to go up. So having that dotted line kind of keeps you in line and makes you, doesn't, allows you to not get carried away with, concave up, because we know it's not going to go up. It's just going to have that curvature down. Okay, any questions there? Does that make sense? Okay, let's do one more of these graphs. I didn't do this in the morning review. I didn't get the chance this morning to do it. But if we can turn to page 5. And let's try this one below so we can kind of get some additional practice with our sketching. So page 6, worksheet 2.
Yeah, you said there are gonna be like 9 topics covered.
Yeah, that's right. It'll be 8 or 9 questions. There may be a repeat in one of the topics, but you have all topics here in front of you. Okay, number 8, let's plot our order pairs. Those are the easiest thing to start putting onto our graph. Again, page 6, number 8. Okay, I've got my 4 order pairs going. Let's translate those statements onto a slope slide line so things will become more visual for us. Okay, f prime of x is less than 0. What's the way of saying that? Yeah, slope is less than 0, so negative. Where is the slope going to be negative? Left of 2 and right of 4. So if they give you x values, go ahead and put them onto your sign line. That they're helping to helping you to fill in those critical points there. So to the left of 2 and to the right of 4. Okay, f prime of 2 does not exist. What's a way of interpreting that? Sharp turn. Okay, great sharp turn there. F prime of 4 is equal to 0. What do we want here? Right. Wherever the order pair is, the slope at 4 we want to be 0. Okay, f prime of x is greater than 0, or x between 2 and 4. What does that mean? Positive slope. Yeah, so I can fill out the rest of my slope sign line. Okay, let's do a second derivative sign line. F double prime is less than 0 for x doesn't equal to 2. Everywhere except 2. Yep, concave down everywhere except 2. Okay, let's do 2 versions of the graph so that we don't try to do too many things at once. I'm just going to follow the path of the graph here. I want a decreasing to a relative min at 2, sharp turn, increases, relative max, slope 0, and then decreases to the right of that. So I'm not going to veer too far away from my path when I get to the cleanup process, but at least this will kind of map out where I'm supposed to go, right? I'm not going to create a new path. I'm just going to follow along the path and give it some cleanup efforts. Okay, so decreasing, I'm connecting the dots here, just going through those points. Decreasing to 2, increases to 4, decrease to pass forward to positive infinity. So now I'm going to go through and give it the curvature it needs, right? So it's going to be concave down. So make sure that you don't do a full U here, because if you do, then you're creating an increase, which is not part of the graph, right? We want the graph to be completely decreasing. So you're only going to show a portion of the concave down. Right? Whole time I'm maintaining that decreasing slope. Sharp turn. And then the rest of it concave down, right? So here I can kind of give it that more full concave down shape because I have an increase and decrease, and I want to slope 0 here. So, but here I have a sharp turn at 2. Okay, questions? Okay, let's go to worksheet 3. Okay, yeah. No, you don't have to. Guys, you don't have to do these sidelines. But if you do make a mistake and you have your sidelines, at least I can try to give you partial credit. And I think it's visually helpful. So it's not required, but I do think it's helpful. And it could benefit you for partial credit. Okay, let's go to page 9, worksheet 3. Okay, so number 1, find the critical points. So all we do with critical points is we find f prime. If there's a need for common denominator, we may need to get that cleaned up, get it to be a common denominator, and then set the numerator equal to 0, denominator equal to 0. But that's it. All we're doing is we're just finding critical points from f prime. Nothing more after that. Okay, so let's find f prime. Okay, go through power rule for both my terms. So 8/5 minus 5/3 is minus 5/5, yep, is 3/5. Okay. 3/5 minus 1, same thing as 3/5 minus 5/5, which is negative 2/5. Okay, let's do some. Yes, question.
We have to combine them before
We can't, because we can only combine these if we're multiplying. Okay, we can't add the exponents with that plus in between. We're kind of stuck.
Okay.
Yeah. Now, if it was x to the 8/5, x to the 3/5, then we can add the exponents. Then we can make it x to the 11/5. But if there's a plus in between, we're kind of stuck. We can't do much with this. Okay, so I got my negative exponents showing as positive exponents. I can clearly see that I don't have the same denominator, so I can't quite merge these fractions just yet. But what is a common denominator that is shared? 5 is not enough. Yeah, I need something large enough that both can go into, right? So we're not quite looking for a common factor. We're looking for common denominator, something that both can go into. So 5x to the 2/5 is going to allow for both of these to go into each other. Okay, balancing our fractions here. What's missing between my old and new denominator here? X to the 2/5. So multiply top by x to the 2/5. So 8x to the 3/5 times x to the 2/5. When I multiply bases, I add exponents. So what's 2/5 plus 3/5? 5/5, which is 1, right? So that's nice. That just ends up being just 8x. Any adjustments with the second numerator? No, keep that 3, right? That's all we need. Okay, so now that I have common denominators, I can push them together into the same fraction. And now I have a much easier time looking for my critical points. I'll set the numerator equal to 0. I'll set the denominator equal to 0. Right, whatever causes numerator or denominator to be 0 is a critical point. Okay, divide by 5, raise both sides to the 5/2. It's going to end up being 0. Okay, so I have 2 critical points. That's all I need to do. I can stop there. Okay, any questions with 1? Okay, number 2, find the values of absolute extrema. So the whole purpose here is to find the highest and lowest points on the graph without the use of a graph, or without looking at the graph, just using really minimal piece of information. So the theorem here is EVT. There's only one condition, is that the function needs to be continuous on the closed bracket. There's no need for a differentiable statement. We can't have a sharp turn. It's okay. We're just looking for highest, lowest points. We're not trying to guarantee slope. You only need that second differentiable statement if we're trying to guarantee a slope, and that's only for Rolle's and mean value theorem. Okay, so the nice thing is there's no denominator. Our function is a polynomial, smooth. It's a continuous function all the way through. So our theorem is EVT, and our function is continuous on the closed bracket there. Okay, so next step is we want to look for critical points, because critical points could also be candidates for peaks and valleys. So let's find f prime. Okay, go through power rule. Factor out of 6. Solve for x. I get 2 and -1. Okay, so we have 2 candidates for highest and lowest points on the graph. But what do we have to do to double check that we can keep both of our critical points? Interval, good. All right, so no guarantee, right? We have to make sure that it's part of our problem. If it's not part of our problem, we have to remove it. Is 2 safe? Yes. Is -1 safe? Yes, we're going to keep both of them. So make sure that you understand we got 4 points to test now. If you have critical points that are valid, you're going to test those, but you're also testing your endpoints. Okay, don't forget to test your endpoints. That's also part of the theorem. So where can I put all these 4 points to test? Original, yep. Because I'm just looking for physical locations of the y values, and the y values will tell me what is an absolute max and what is an absolute min. They all get used, plugged into the original function. I'm just gonna speed it ahead here. You can use your calculators tomorrow. And all I care about is the y value. Okay, absolute min is -19. Absolute max is 8. That's it. Just give me the y values. Yeah, if I say absolute extrema, that's an indication that you're doing EBT. Yeah. But the other ones I'll name. If it's Rolle's theorem, I'll name it. If it's mean value theorem, I'll name it. Here, I won't name it, but you have to name it yourself. Extreme value theorem. That's right. Everything else is relative. Yeah, the second page will be all relative extrema. Yeah.
And for finding the absolute extrema, we don't have to like do the long condition. It's just absolute maxes, then absolute min.
That's right. That's right. You don't write your because statements for here. No.
Okay.
All you, but your justification is your work, is your continuity statement. You're testing all the critical points that you need to test, and then tell me the max and min, and that's justification. Yeah.
Okay.
So no because statements needed for EBT.
Okay, that makes sense.
Okay. Everybody good? 1 and 2. All right. Number 3. Okay. So for our function, on the closed interval from -1 to 3, determine if Rolle's theorem can be applied. So let's think about what Rolle's theorem is. Rolle's theorem is asking, where is the graph going to experience a slope 0? And if there is, can we guarantee it and can we find it? Okay. So Rolle's theorem, now we're trying to guarantee a slope. So we do need a couple of statements here. We need a statement about continuity. We need a statement about differentiability. But there's a potential red flag here that could disrupt our conditions. And what do you notice about this function? That denominator. Because there's a variable in the denominator, which means that there is a break in the graph. We need to check to see if that break is interrupting our interval, because if it does interrupt our interval, we can't go through. We have to just stop and say function not continuous. So what do you notice here? What does that x plus 2 tell you? Yep, where's the vertical asymptote? -2, right? You set that x plus 2 equals 0, go -2. Okay, so -2, there is a break in the graph, but is that break going to disrupt my interval? No, it's safely outside of it. Our function is continuous on the closed interval, and 95% of the time, if our function is continuous, it will also pass the differentiable test. There is a couple of exceptions, but I'll talk about that later. But for now, let's just think, all right, if I can get it to pass the first test, I know my second test is good to go for now. Okay, so I'm going to be asking you to state your conditions. Continuity is with brackets, differentiability is with parentheses. Now, there's one more condition that Rolle's theorem requires, is if I need slope 0, there's something special I need to happen with my order pairs at the endpoints. And those order pairs have to share the same y value. I need those endpoints to be directly across from each other so I can draw a horizontal line between them. Okay, so let's gather some information here. We're going to find f of -1. We're going to find f of 3. We need to know what is happening at the endpoints. You're going to see that Rolle's theorem and mean value theorem are almost identical. It's just that Rolle's theorem is a bit more restrictive because it requires the same values out of the endpoints. Okay, so -1 into the original function. Again, we're not touching derivative yet. There's quite a few things we need to do at the function level. So make sure you do all that before you do the derivative. If you do the derivative too soon, I see students tend to run into some mistakes because they start doing things with a derivative that's not quite what we're looking for. Okay, so you gather your information here first, and then your second half of the problem, you can worry about the derivative. Okay, so -1 into the original function, I get -1 squared, which is 1. 1 plus 2 is 3. 3 minus 3 is 0. 0 over 1 was 0 over 1. 0, right? So 0 over a non-zero is still a 0. That's a real number. Okay, 3. 3 to the function, I get 9 minus 6. That's 9 minus 6 is 3. 3 minus 3 is 0. 0 over 5 was 0 over 5. 0 as well. Okay, now, does it pass Rolle's theorem? Yes. And what is this? What information can we gather from this information from these ordered pairs? The slope is what? 0. Okay. It's not because that these have to be 0. It's because these are the same numbers, right? If it's 7 and 7 or 9 and 9 and 8 and 8, I'm still going to get slope 0. I don't want to just translate this number over here, right? That's something else. Okay, so I know I have slope 0. Let's find our f prime. And if I want to find f prime, look at how this problem is set up. I have to go through what? Quotient rule. Okay. F prime g minus fg prime. All over g squared. Okay. Don't cancel out. To spend the time to distribute all this here. Okay, I want to know when slope is equal to 0, so that 0 is going to go in for my f prime, and I only care about the numerator. The reason why is because my denominator would tell me slope undefined. I don't care about slope undefined. I want slope 0. So I'm just going to focus on the numerator. Now, unfortunately, this is not factorable. On the quiz, I will give you something that's factorable, but here we have to go through quadratic formula. Okay, so now there's actually two values hidden in here. There's a c equals -4 plus root 20 over 2. And there's also c equals -4 minus root 20 all over 2. Okay, now if I enter this in the calculator, what am I looking for? How do I know whether to keep either one of these? Where do these have to be? Inside, right, inside the interval, right? So if I enter -4 plus root 20 over 2, that will give me a decimal value that is safely inside the interval. So I'm going to keep this one. But if I do -4 minus root 20 all over 2, that's going to be a negative value. That's going to be outside of my interval. Not going to use this one. So quadratic formula, not going to be on the quiz tomorrow, but the process is still helpful, right? We understand how to move through this process. Okay, any questions with Rolle's theorem? Okay, mean value theorem, almost identical. The only thing is, your continuity statements will stay the same, differentiable statements stay. You're still going to find your order pairs, but the y values, do they have to be the same? No, but you're still going to find the slope, right? And the slope doesn't have to be 0. It could be 0, but most likely it could be like 1/2 or 2 or 3 or 5/5. Whatever it is, you're going to find that slope instead of equal to f prime. Okay, we got through a large portion of the types of problems that you're going to see. I encourage you guys to work through the rest of worksheet 3. Tomorrow morning, I will go over the morning review. But the morning review is kind of short, so I'll probably spend time revisiting some previous topics. Okay, don't forget your phones.
Yes.
It's like sort of
And he's not great at all. He's actually not great at all.
we know you just. Yeah, I was on my page.
He's getting